So we're going to do the same thing. We have a body in motion, and this is actually this is still just a flat plate, but I want you to just maybe appreciate that, like, if you zoom in close enough, everything looks like a flat plate. So these are still good ways to approximate what's happening close to the surface. So I want to tie together this momentum, thickness, and shear. So, and you're trying to find the shear stress out the wall. So what's the skin friction of the actual body? Again, that's what we're super concerned about, because that viscous force, there's more force than we sometimes accounted for, because we have to account for overcoming the viscous forces of the fluid. And that is what we're doing with this boundary layer stuff. So if you zoom in, you are probably so sick of me drawing this picture. But I love drawing pictures, so why not? So that's the shear at the wall. Y, X. This is some function u of y that I'm looking for. And there was the fluid that's not moving. So there was displacement physics that talked about it, etc. Well then, so let's look at the change in kinetic energy has to be done is equal to the work done on the system. That would be the viscous force times some length. It's work is force times the distance. So the change in kinetic energy has to be that, right? That viscous force times a certain length, right, over it. So change in kinetic energy actually was related to this momentum thickness, because that's what we were talking about before. So then you get this cancellation of this, you get the W, classic relationship that width. That's the width in and out of the board. At a point, right? Again, momentum thickness is at a point as well. So we have that the skin friction at a point is this, the right, some width outward, a line just of width. Notice that the L canceled out, meaning it's point-wise. So really it's just one little line, the width, speed, and that momentum thickness. This is a function of X, remember. The displacement thickness and the momentum thicknesses are all defined at points along a surface. So we can then ask, well, what's a little bit of change in the viscous force? Well, a little bit of change in here would really be the shear with dx. That's just, right, this is just force is a pressure times an area. Right? I mean, it's, right, so this little bit of change in this force moving this block is the same as this shear pressure times the area. So think of this as a dx now. So if there's shear here, pressure times area is a force, so that makes sense. And then you have that df dx that. So, right, another thing you do is you then solve for this. This is a very important equation for a computer or with something else, because again, now what I've done is I've written out the equation for the shear stress at the wall. That was the thing I cared about, and it's dependent on this momentum thickness, which is defined in terms of boundary layer thicknesses. Right? So it's a whole lot just to get this idea of what in darn heck is the shear happening at the surface of my external flow. But this is a great one to be at because, again, it's hard to remember what this momentum thickness is, but just you have to appreciate that what it is it's just an integral that you are free to calculate. Okay. And same with the displacement thickness. It won't pop up until later, actually, when we talk about curved surfaces. But for a flat plate, the shear stress at the wall is dependent on this momentum thickness. For a curved plate, there's going to be another term in here that involves the displacement thickness. And it will involve this, and it will involve this. So this is for a flat plate, but for curved, we get another term. But we're not there yet. But for flat plates, we have a nice, simple expression for what the shear stress at the wall is, and it's based on its momentum thickness. So if you're lazy, right, and you just want to get an idea, what you can do is you can just say, you know what, I know what the velocity profile is on this picture I've drawn 800 times at this point. Right? You're going to say this is parabolic. You're just going to say you know what it is. It's at U infinity. So you're going to write some parabolic function that satisfies this. So wait, they go 2. That's one way to do it. Or this is the delta as well. Again, the way you write these is in terms of a delta, in terms of a boundary layer itself. But that's just right. That's what you do. But that's the idea of this. Sorry about that. Of why this is a good expression, because you can just sub something in for this and get a quick idea. So your book has a table of assumptions, like it's a cubic u of y, a sine of u of y, or other ones. But just like how to get a bunch of expressions for internal flows, we had to sub in the u of r to get expressions. It's the same thing happening here. We just need the u of y. Now Blasius, has the exact relationships. Right? These exact relationships are actually coming from numerics. That is because we can't be based on you, right? We can never actually write out what this equals, the exact form of it, based on the ODE that Blasius derives. But you can write down the ODE, and then you can use a computer, even back then, or like tables of integration to ask these questions. So Blasius has an exact ODE that represents what u of y is, not the boundary layer equations, because like I said, what we did was we went to a stream function, then it derives the stream function equations. Stream function gets them to u, that being done. So the exact results are technically numeric results that he just looks at a table and he gets the coefficients that I listed earlier. Sort of, right, so there's a flip where the approximate results are almost like are mathematical or analytic, because what you end up doing is you just sub in a function and do this integration yourself, or have Wolfram Alpha do it. I don't care. But that's a important part. So this looks daunting, but right, you can get an idea of your shear stress if you make the assumption of what the profile looks like. This does not, right, so this is all solved for the flat plate, because again, Blasius did that, where he figured out an ODE that governs all of it and then wrote them down. So now you get the sense, right? So for the boundary layer thickness over whatever x I'm at, first big one. Second one, (332). another result from Laplace where he just does that momentum integral thing, right? And you get this, you get this relationship. And then the other one we get is a displacement thickness, which is exact as well. I need to check if I have the right constants. And then we have momentum thickness over x. This is and those are more, and there's more ones too. There's like pointwise shear. There's like a pointwise coefficient. I had another one in there earlier. Look at the notes, look at your books. But those are what we're getting at when we get these equations, or what we're trying to solve for. And I'm gonna. The other one I really want you to have is. Right, and we even get what I think is the most important one for a flat plate is the skin friction coefficient. So you have boundary layer. Again, this is by x naught, so this is variable for an x. Boundary layers are all functions of x, so you have to put that in there. Shear stress as a function of x as well, so this is along. This comes from that momentum integral. Displacement thickness doesn't really matter yet, but we can get to it, and then the momentum thickness. So I hope that motivates where all these Reynolds numbers, -1/2 equations come from. And most challenging, I guess, would say for what you calculate is just realizing when you have to calculate Reynolds with respect to where you are at a point, or where you have to calculate Reynolds number for a whole plate. And just keep track of this sub x naught, sub x, or sub L to keep that straight. And the other confusions that happen is what constants to use. So these are the Blasius constants. They're exact, but you can do approximate ones, and then you can get basically sort of the same equation, similar answers. They'll be slightly different, but please use the Blasius constants. If you want to try out and do all of them, just be very exact, and maybe in homeworks of what constants you're using. I hope I will also rescan my notes for the error I found embarrassing. Okay, up next, the turbulent boundary layer.